Hello everyone, welcome back to another discussion dynamics. I hope you're doing well. The topic of today's discussion is work energy methods. This is exactly what you can see on the board. And here is where we are on the timeline. The plan for today is following. We will start with a brief lecture overview, and then we will do two examples. Example number 1 and example number 2. Without further ado, let's dive straight into our discussion. Let us start with a brief lecture review. So, last time we derived this expression. I hope you remember. So we started with F equals to ma, and we just said that this expression, that this force, is a net force. In other words, this force is a sum of all the forces acting on our system. And then, with a couple of algebraic transformations, we ended up with such expression. T1 plus u12 equals to T2, where u12 was work of all the forces. Today, we will divide these forces into two groups. So last week we had F equals to ma, but today we will just divide F into conservative forces and non-conservative forces. And if we follow exactly the same transformations as last time, we will end up with work of conservative forces plus work of non-conservative forces, and this is equal to kinetic energy at the end minus kinetic energy at the beginning. This expression can be expressed as V1 minus V2. So this is a difference in potential energies at the beginning and at the end. And this expression is just work of non-conservative forces. So this is u12 non-conservative, work of non-conservative forces. So as you can see, we ended up today with an equivalent form of this expression. So we ended up with T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. This expression and the expression from last week, so this expression, they are equivalent. Just in here, we look at work of all the forces, and in here we just divide forces into conservative and non-conservative. In this course, we unfortunately do not require from the students to know the difference between what the conservative force is and what the non-conservative force is. In this course, we just would like you to know what are the examples of each of them. So let me scroll down the board and I will share with you some of the representatives of these two groups. Let me start with conservative forces. So first thing that comes to my mind is gravity. And force associated with gravity is mg. And potential energy will be mgh, where h is obviously an elevation of our particle. Another example of conservative force is spring, linear spring. Linear spring. The force associated with such force, with such spring, is k delta, and the potential energy is 1/2 k delta squared. In this course, you can also run into cubic springs. And the force associated with such spring is k delta cubed, and the potential energy is 1/4 over k delta to the power of 4. I believe that only these three forces are conservative in this course. When it comes to non-conservative forces, I believe that the first thing that comes to your mind is friction. Kinetic friction. So our Tf is equal to mu k n. Another example can be applied force. So just F. That force can change in time, it can change with position, it can be sinusoidal, it can be constant. It's just an applied force. And the third example that you can run into during our course is aerodynamic drag. However, you will run into it very rarely. And the force associated with the aerodynamic drag is some constant times velocity squared. And if you would like to calculate potential energy, work of such forces, so you want to non-conservative, you just must follow the strategy from last discussion. So basically you must integrate from the beginning to the end of you must just calculate such integral, where f is naturally one of these forces. Also, there is one more non-conservative force you can run into this course, which is reaction force. However, you all know that work of reaction forces in this course is 0. Because we are dealing in this course with so-called smooth constraints. So I am 99% sure that work of every reaction force you are going to run into this course, the work of such force will be 0. For example, work of normal force is 0, if you recall from the last discussion. Okay, I think that's it when it comes to this brief lecture review. I have honestly nothing else to add. Okay, so I think that now it's time to do example number 1. Let's do it. Feel free to pause the video and read and understand the problem statement before we start our solution. So what do we have in here? We have a small block that has certain mass, I believe. Yeah, we must assume that it has certain mass, m. Our block has velocity 0, and it moves along this conveyor belt, yes, or actually it slides along this horizontal surface with velocity v0. We also know that the height of this horizontal surface is h, and what they ask us for is to find angle theta at which our block loses contact with the cylindrical surface BCD. So these are our knowns. Velocity 0 is 8 feet per second. Our h is 3 feet. And they ask us to find theta at which our package loses contact with the surface. I think I can arrange this in a better way. Okay, so now even though we haven't started the solution yet, I think that I just would like to ask you to pause the video right now, and I would like you to think about the requirement in our course for losing the contact with the surface. In other words, what has to happen in our system so that our particles lose contact with the surface? Feel free to pause the video right now and think about the answer to that question. All right, so for those of you who got it right, congratulations. And for those of you who just came here to put their notes together, obviously what I have in mind is that normal force has to be equal to 0. So as you can see, even though we are in work energy chapter, we will actually start our solution with kinetics. And a little bit of spoiler alert, work energy will be second part of our solution. So what was the recipe in kinetics? I believe that we should start here with FBD and KD for our particle. And let's draw this FBD at arbitrary theta. So let's say that our particle is basically here at point C. Okay? So I believe that I would like to represent our particle with such a rectangle. Oops. I think that this is our trajectory. No, actually, maybe it's better if it's not filled out. This is our trajectory. And this is our arbitrary theta. Let me copy paste this drawing to our kinetic diagram. And now let me show you what forces act on our particle. mg and normal force. I think these are all forces acting on our particle. Now let's focus on kinetic diagram. Since this is a curvilinear motion, I would like to go for a curvilinear coordinate system. I'm going to choose NT coordinate system. So MAN will be pointing this way. And let's say that our tangential component will be pointing this way, MAT. Okay, and now in the second part of our solution, we should write down equations of motion for tangential direction and also for normal direction. Okay, so what happens along the tangential direction? Aha, I must project mg onto this direction and onto this direction. So if theta is here, I believe that definitely theta will be here as well. And that means that our theta is here. So this component will be mg sine theta, and this component will be mg cosine theta. Okay, I am ready to write down our equations of motion. So in here we will have mg sine theta, and this is equal to mat, and on the n component, in the n direction, I will have mg cosine theta minus n, and this is equal to man. So basically, my goal in here is to find expression for n, because I hope that you remember, we would like to find expression for n, and then we would like to set up n to 0. So I think that all of you know which equation I'm going to go for. I'm going to go for this expression. And also, before doing that, I just hope that you all remember that since we are in curvilinear motion, I can set up an to v squared over rho, where rho is a radius of our curvature. And in this case, rho is constant. Rho is equal to h. Since this is h. I know that all of you see that. This radius is h. Okay, so what do we have in here? We have expression for n. N is equal to mg cosine theta minus m v squared over h. And this is expression for arbitrary theta. However, we do not care what happens at arbitrary theta. We care what happens at very specific theta that our n is equal to 0. So we can write that 0 is equal to mg cosine theta, but this is a specific theta. So theta at which our particle will lose contact with the ground. So let me call it theta star minus m v squared over h. However, so basically our theta star is not known, but this is not the only unknown in this equation, because actually our velocity is also changing. Please, I hope that you don't mind if I scroll up the board. Please observe that our velocity is v0 along this horizontal surface. However, once our body is sliding on that cylindrical surface, its velocity will also start changing. Velocity of our body will no longer be v0. I think it will start increasing. So you can see that at some at some theta, let's say theta star, our velocity will not be v0, but I don't know, let's call it v star maybe. So v star will be a velocity at which our particle loses contact with that cylindrical surface. So let me plug in that v star into our equation. So this is no longer v, but this is v star. Okay, so it looks like we ended up with one equation and two unknowns, which is not solvable, at least right now. We need one additional equation. And probably some of you are thinking that we should go for this equation, and they are right. You are right. If you would like to use this equation to provide that additional information about our system, you are correct. However, as you can see, we are looking. My goal right now is to find v star, and in here we have our acceleration along the t direction. So basically, we must integrate this equation once in order to get to the velocity level. We could do it, why not? However, we can actually go for a ready-to-go integrated equation, which is exactly work energy method for this particular problem. Please recall the brief lecture review from the previous video, where I basically took F equals to ma, I projected it on the trajectory, and I integrated once. This is exactly what you should do in here. And if you do that, you will actually end up with such expression. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. So this is our part 2. It would be work energy method. Okay, so now our goal is to find these 5 expressions. T1, V1, T2, V2, U12 non-conservative. Okay, so you can feel free to pause the video right now and find expressions for T1 and T2. I can even copy paste the drawing from the drawing we started with. So let me just take this drawing and copy it here so that your job is slightly easier. So again, feel free to pause the video right now and find expressions for T1 and T2. These expressions are naturally 1/2 m v0 squared and 1/2 m v star squared. Now, if you would like to, you can again pause the video and find values for v1 and v2. Okay, so for those of you who did it correctly, congratulations. And for those of you who just came here to put their notes together, these are the expressions. However, before showing you the expressions, we must specify the datum, right? So I would like to put datum here on this elevation. This is my datum. So with such datum, we can see that our V1 is mgh, right? Because at configuration 1, which is this configuration, by the way, our elevation is h, and at configuration 2, which is, by the way, this configuration, this is our expression, this is our elevation. And this elevation is exactly h cosine theta star. Actually, maybe I can do it in a similar way. H cosine theta star. How do I know that? Because I know that this vector is h, and if you have a look at this triangle, this green triangle, actually this green right triangle, because in here we have a right angle, you can clearly see that this side has length h cosine theta star. So this potential energy will be mgh cosine theta star. Okay, great. We have 80% of the problem done because we found T1, V1, T2, and V2. Now let's focus on U12 of non-conservative forces. So I think it will be 0, isn't it? Because the only non-conservative force FBD for non-conservative forces. Actually, I can scrub the board, right? Because I have FBD already here. Or I can redraw it. Or copy paste maybe. So we can see that the only non-conservative force is our reaction force. N. And you all know that work of reaction forces is 0. That's why our work here is 0, because we have no friction in the system, and there are no applied forces act on our body. No applied forces. Okay, so it seems like we have 100% of the problem done. So now we should plug these 5 expressions into our original equation. Let me do that for you. So basically I have to take this expression and I have to represent it in such way. So I believe that T1 was 1/2 mv0 squared. The initial potential energy was mgh. Work of non-conservative forces was 0. Our final kinetic energy was 1/2 mv star squared, and final potential energy was mgh cosine theta star. Okay, I think that m's cancel out, and we can find expression for v star. V star square is equal to v0 square plus 2gh minus 2gh cosine theta star. So this is our expression for v star square. Let me show you where we left our solution after part 1. So this is where we left it. So right now, I think that all of you can see that we just must plug this expression, this expression here. And we will end up with 0 is equal to mg cosine theta star minus m v0 squared h minus 2mg h plus 2mg, no h, sorry, 2mg cosine theta star. I believe that m's once again cancel out, and I think that this expression is exactly the same as this expression. So we will actually end up with 0 is equal to 3g cosine theta star minus v0 square h minus 2g. So our theta star will be arc cosine 1 over 3g times v0 square or divided by h plus 2g. And if you plug in values and grab your calculator, you will obtain that our theta is approximately 27.44 degrees. And this is the answer to our problem. So this is the angle at which our particle will lose contact with that cylindrical surface. Okay, this is the end of example number 1. I hope I explained everything clearly. If you still have some questions, feel free to post them on Piazza or come to our office hours and we can talk about that problem during our office hours. Now I would like to do example number 2. Here it is. Here is example number 2. So as usually, feel free to pause the video right now and read and understand the problem statement before we start our resolution. Okay, so what do we have in here? We have our color here, and that color has weight, has mass 10 pounds. The color weighs 10 pounds. And it is at rest at this position. And somebody just nudged it a little bit towards the right. And that little nudge causes the motion of the color along this circular bar. So our color starts its motion at point A and it ends its motion at point B with certain velocity. Let's call it, I don't know, VB maybe? Why not? So at point B, our color has velocity VB. It of course, this color will go further along that circular bar, but we just care what happens at that point B. What else do we know? We know that there is a spring attached to our collar. And if I remember correctly, that spring is undeformed at this position. But you can see that at position B, our spring is stretched. Moreover, there is a constant force Fc that opposes the motion of the collar. And what do they ask us about? What do they ask us for? Oh, they ask us to find the load applied by the collar to the circular bar as it passes point B. So again, in here they ask us to find normal force acting on the circular bar. So since they ask us to find the normal force again, I think that it's natural to start our solution with kinetics. So again, I will just draw FBD at configuration. So at configuration B, and also I will draw a kinetic diagram. By configuration B, I mean, of course, this configuration. So this is our particle, and this is our trajectory. Let me copy it. Let me copy it here. So what forces act on our color as it passes through point B? I believe that definitely there is mg acting on our color. I believe that there is a reaction force coming from the circular bar. I am pretty sure that there is that constant force Fc acting on our system, and also there is force coming from this spring. So this will be, let me maybe use green color for that. So this will be force, let's say Fs. Let me put it maybe here. And this is that angle, I think phi. Yes. Okay. Now again, this is our trajectory. Which is clearly curvilinear. Our trajectory is a circle. So again, I would like to go for anti-coordinate system. So our MAT will be pointing this way, and MAN will be pointing inside the circle. Okay, so I think that we are done with FBD, and we are also done with KD. Now we should focus on equations of motion. So we should write sum of forces in the t direction and sum of forces in the n direction, where this is positive direction and this is positive direction. So what happens in the t direction? Aha, in here we have mg minus fc, and also we must project fs onto these two components. Let me use red color to do that. This component and this component. So we need this vector and also this vector. So this one will be fs cosine phi, and this red vector will be fs sine phi. Minus fs sine phi, and this is equal to mat. So now let's focus on the n direction. So in here we have minus n plus fs cosine phi, and this is equal to man. And again, we can replace an with v star over rho. However, our rho is constant, and our v at point B is vb. So it would be vb squared divided by r. Great, I think we found expression for n, because n occurs only in the second equation. So we have n equal to fs cosine theta, not theta, cosine phi, minus mvb squared over rho over r. Okay, so how many unknowns do we have? We definitely do not know n. We definitely do not know velocity of particle at point B. I am afraid that right now we do not know what is the force coming from the spring, and also we do not know phi. So we have one equation and four unknowns. However, I believe that we are able to figure out the values of Fs and theta. Let me do it on the side. I would like to do it here. So let me focus first on phi. I think we need some drawing here. Let me take this drawing and copy it here. So I believe that phi can be found from this triangle. Here, here, and here. Because this side is R and this side is H. So I think that tangent of phi is equal to H divided by R. And I think that we know what is H, and I think that we know what is R. Let me scrub the board. So our H is 0.75 and our R is 1.75. So our phi is equal to invert 10 of 0.75 divided by 1.75. And if you grab your calculators, you will obtain that our phi is approximately 23.2 degrees. Okay, so we have our phi. So our phi is 23.2 degrees. So I will just mark it with black instead of with red. And now let's also find Fs. So the question is, what is Fs? So our Fs will be spring constant times the stretch in the spring. So I believe that our delta is current length minus initial length, where our initial length, L0, is here. It will be blue. This is our the initial length of our spring. So I think that L0 is R minus H. So this is 1.75 minus 0.75. So our L0 is basically 1 foot. Okay, how about L? L is this distance, this black distance. So I think that our L, since this is a right triangle, our L will be square root of R squared plus H squared. So this will be 1.75 squared plus 0.75 squared. And if you grab your calculators, you will obtain that this is approximately 0.904 feet. Okay, I think that right now we are able to find the value of Fs, since we know, oh, but first, oh, sorry, no, my mistake. Hold on. this is not 0.905 but 1.904. This is the correct value of L. So now our delta is L minus L0, and this is approximately 0.904 feet. Okay, sorry for that. And now we are able to find our Fs value, because Fs will be K times delta. I forget the value of K. Let me scroll up the board. K is 30, as you can see. So this will be 30 times 0.904. And if you grab your calculators for the third time today, you will end up with following value. This is approximately 27.12 pounds. Okay, so as you can see, we found the value of Fs. This is 27.12 pounds. So since value of Fs is known, I'm just going to mark it with black. And all of a sudden, we do not have one equation and four unknowns, but actually we have one equation and two unknowns. And our VB, we will once again find if we go for the work energy approach. You can also, of course, you can also integrate this equation, but this approach is basically equivalent to what we are about to do. So in the second part, we will focus on work energy method. Part 2, work energy method. So again, I'm going to write down this expression, T1 plus V1 plus U12 non-conservative is equal to T2 plus V2, and we will just find these five expressions, T1, V1, T2, V2, and U12 non-conservative. Let me copy the drawing from above. I would like to copy this drawing. So now we all see what is going on in the system. So I think that the kinetic energy at the beginning is 0 because our system starts from rest. In the end, our kinetic energy will be 1/2 m VB VB squared. How about potential energies, V1 and V2? If you want, feel free to pause the video and find potential energies in our system. Just a heads up, I will place my datum here. Now feel free to pause the video and find V1 and V2. Okay, so here are the correct values. So at first, our body is at this elevation. So our potential energy will come only from gravity, actually. So let me write that, because in this system we have actually a spring. So in here we can write V1 gravity plus V1 spring. However, our spring at configuration A or configuration 1 is at its rest length. So we can actually eliminate this part, and our potential energy due to gravity will be mgr, because this is our elevation. How about second configuration? So in here we will again have V2 due to gravity plus V2 due to spring. And right now we can see that our body is aligned with our datum. So in this case, our V2 due to gravity will be 0. But our spring is stretched. So in here we will have 1/2 K delta squared, where delta was calculated by us earlier. So this expression will be 1/2 times 30 times 0.904 squared. Okay, so again, 80% of the problem done because we found T1, V1, T2, and V2. Now we should focus on U12 non-conservative. So again, I hope that you don't mind if I just draw FBD at arbitrary theta and I look only at the non-conservative forces. So this is FBD at arbitrary configuration. So let's say that this is our trajectory. And let's draw our body here. And the non-conservative forces acting on our system are normal force and also Fc. The other two forces will come from gravity and spring. And they are conservative, so I'm not going to include them here because these are only non-conservative forces. Okay, so in here we will have work of Fc plus work of normal force. However, I think I already mentioned it today that work of reaction forces in our course is usually 0. So we can just focus on work of Fc. Let's put it in more mathematical form. So I think we can write down such integral from a to b of Fc times ds. And I also hope that all of you see that our ds is always pointing in the opposite direction than Fc, because our body moves this direction. So actually our integral will look like that. Integral of minus Fc ds. And now the question is, what are the integration bounds? So point A is here, and point B is here. I think that easily we can associate 0 with point A, and this curve length, this arc length, is, I believe, r times pi over 2, because this angle is 90 degrees. This is a right angle. Okay, and if I remember correctly, our Fc was constant. Let me scroll up the board just to confirm that. Yes, that's true. Fc is a constant resisting force, as you can see. So that integral will be easy. So that means that our integral will be equal to minus Fc r pi over 2. So that means that our u12 non-conservative is equal to minus fc r pi over 2. Okay, I think that we found these 5 expressions. We solved 100% of the problem, right? I believe so. So now we should just copy this expression and fill it out with our findings. So T1 was 0, V1 was, I believe, mgr, work of non-conservative forces we just found, it is equal to minus fcr pi over 2. Kinetic energy at the end was 1/2 m vb squared, and potential energy at the end was 1/2 30 times 0.904 squared. Okay, let us find values to each of these expressions. So I believe that this is 17.5 joules. This is approximately 1.374. This is approximately 0.155 VB squared. And this is approximately 12.258 joules. So our VB will be equal to square root of 1 divided by 0.155, 17.5 minus 1.374 minus 12.258. And if you grab your calculator, you will obtain value of VB that is approximately of 5 feet per second. Okay, great. We found velocity at point B. Let me now go back to part number 1, because this is the equation we left there. Right? There was one equation and 2 unknowns. However, right now we found the second unknown. So our VB is all of a sudden known. Oops, sorry for that. Our VB should be plugged in here. And if we do that, we will see that our N is equal to 27.12 times cosine of 23.2 degrees minus 10 divided by 32.2 times 5 squared divided by 1.75 feet. If you grab your calculators for the last time today, you will obtain that our normal force between the collar and the circular bar is approximately 20.502 pounds. And this is what they ask us for. The collar acts with such force on the circular bar. Okay, I think that's that when it comes to this discussion. I hope that I managed to explain everything clearly. And again, in case something is unclear in here, you are more than welcome to ask us questions either on Piazza or during our office hours. Yeah, I think I have nothing else to say today. So thank you for your attention and see you next time. Bye.